Hi everyone, welcome to the Camaraderie Hall, the Brain and Creativity Institute. As always, I want to start by thanking USC Office of Research for funding this series, and also Antonia and Hannah for allowing us to use this auditorium. This is the last talk of the series. We'll continue the series next year, hopefully with 2 or 3 more speakers. If you have suggestions for who we should invite, please email me and let me know. I've already received a couple of suggestions. Also, we're going to have our grad social next week on Friday at the faculty club. If you're interested, send me an email to RSVP. We're pleased to have Justin Grimmer here. Justin is currently an associate professor of political science and computer science at Stanford University. He received his PhD and master's from Harvard in the Department of Government. Justin's research examines how representation occurs in American politics using new statistical methods. His first book, Representational Style in Congress, What Legislators Say and Why It Matters, Cambridge University Press, won the Fino Prize from the Legislative Studies section. His second book, The Impression of Influence, How Legislator Communication and Government Spending Cultivate a Personal Vote, Princeton University Press, demonstrate how legislators ensure they receive credit for government actions. Please join me in welcoming Justin.
So thank you for the introduction and thank you for having me here today. I'm really excited to present this work to you and would love if you have questions, if you just shout them out, go ahead and interrupt me to make sure we're all on board as we go through the talk. All right? So this is a collaboration with my grad student, Christian Fong. And what we're interested in this paper, and indeed in this project, is answering a question that social scientists ask a lot. So how does X affect Y? That's a very basic question. And we have lots of methods to answer that sort of question. What's interesting, we think, about this particular project is that we want to think about a different kind of X. That is an X that is high dimensional, something that's encoded in natural language. So I'm going to give you some examples of this just so we can sort of set the scene so we can understand what I might be talking about. So on a nearly daily basis now, we have interventions performed upon us with okay, that's good. I was wondering why. There we go. Funny images and nobody was laughing. I was like, oh. Joke failed, tough crowd. So on an almost daily basis now, we have interventions performed upon us where we have text coming from a particular political figure that is perhaps eliciting a variety of reactions. It could be emotional reactions from the public, it could be moving media's agendas. In many ways, we're interested in knowing how do things like Trump's speeches and his tweets affect a variety of political and economic outcomes, even businesses, which he recognizes the power to do as well. Of course, this didn't start with Trump. We may also be interested in how presidents of a more sort of standard usage of power may use their bully pulpit in order to move public opinion or to focus attention on a particular set of issues. Of course, it's not just text either. We may be interested in how things like campaign advertisements combine text and music and images in order to elicit particular reactions and to persuade people to vote a particular way or not in an election. And as a public as well, we think that maybe our sort of text-based or speech-based actions maybe have some effect. So there's been a recent resurgence in the importance of town hall meetings in a way that perhaps we haven't seen in 20 to 30 years in American politics. This really began with the Tea Party movement, which during that August recess in the first year of the Obama administration, they made very clear to congressional Democrats their unhappiness with the pending healthcare legislation. And we've seen this again, this resurgence again, with what we might call the Herbal Tea Party, this group of people who are objecting to a variety of actions that are coming out of the Trump administration and using town halls as a place to make clear to their elected officials their unhappiness. But again, we have this situation where people are expressing themselves and eliciting some reaction. And as social scientists, we might be interested in understanding when someone makes a speech in the town hall, what effect does that have? How do we understand its interaction? And indeed, my sort of entry into this, or the reason that this was something I became interested in, was my work on credit claiming. So here we see Richard Shelby. He is the fellow on your right, and he's breaking ground at Shelby Hall. And it's called Shelby Hall not because Richard Shelby is a particularly rich person, but because he, as a United States Senator from Alabama, has secured a bunch of money to help build this hall. And he has made the case that he deserves credit for this money being allocated, even though there's many ways in which the government, many levels of decisions for the government to allocate this money. And the running example we'll talk about today are features of a candidate's background or their biography. So here we have John McCain in his fighter jumpsuit. And these features of a biography may affect the way people evaluate candidates. And so across all of these examples, we can state sentences that says something like, we want to know the causal effect of some text or some speech or some image or some other high dimensional thing. And you may be thinking there's a whole architecture in order to uncover these causal effects. Indeed, we might all imagine experiments that we could hypothetically run in order to uncover these causal effects. And a different sort of feature of this project is that we're not just going to credibly estimate these interventions, the effects of these interventions, but rather we're also going to go out and try to discover the sort of features of the text that affect the responses. What are the low-dimensional aspects of these texts that are eliciting the response? And so we can get a better sense of that. Let's focus in on the running example for the talk and the running example for the paper that we circulated as well. And so the question that we ask here, that social scientists might ask, is how do voters evaluate candidates? This is obviously pressing for a number of reasons. If you're a political scientist like me, this is a sort of bread and butter question for understanding how representation works. So we think that there's some things that are obvious. Candidates have policy positions and partisan affiliations, and this will get us pretty far in understanding how voters think about these candidates. But there's other things about candidates that voters care about as well. For whatever reason, being a business person seems to matter a lot, at least within certain parties in the United States, and that offers some sort of gravitas when you're making arguments. And we may think that there's other things as well. So we might ask, what biographical facts affect voter evaluations? And so if you're a social scientist, you may go out and try to find this a number of ways. The default tool, certainly within political science at the moment, is the survey experiment. And so here's one potential survey experiment that we might run. The potential survey experiment we might run could be something like the following. We could generate two documents. One document will describe a lawyer who has who attended Yale Law School, so a prestigious law school, and worked with low-income residents. And this other document could describe someone who served in the Vietnam War. And what we could do is we could randomly allocate these documents to people who are taking our survey. We could elicit some response to them, say on a scale of 0 to 100, how do they feel about this candidate? Where 100 is more warm towards the candidate, 0 is colder, so like a feeling thermometer outcome. And then we could take the difference between the evaluations and the biographies, and that would give us a sense of which biography was more preferred by the voters. And that is a pretty standard A/B test that happens a lot in industry. So a lot of optimization that happens on websites and design happens exactly through that kind of randomization. Of course, from that, it's difficult to generalize to underlying features of the text. We don't know why it is that someone may prefer the Yale Law School graduate to the Vietnam War veteran. And so we'd like to, as social scientists, know something else about the underlying features of the text. And so the default way that people tend to do this within the social sciences is to construct nearly parallel versions of a text and then trade off one simple thing that provides information, some dose, some difference between the two. So for example, we might have this top biography here that describes someone who attends Miami University and reads relatively right-wing economists. And then the second condition could describe someone who attends Miami University but also reads as if they had gone to Berkeley, right? And so then this design is nice because it's going to isolate the feature of the text or the treatment. And so we know what's going to be driving the response. We know that it's the difference between these two is the only thing that could be explaining the differences between these two texts. But this supposes that we know what features of the text that we want to manipulate, that we know beforehand what are the things that we want to make an intervention on. And so you may think that that's like a sound feature of theoretically driven research, but if we're thinking at a very early stage in the research, then we may not know what these features are. And instead we may seek out and try to understand what are the important features that we might manipulate. And yeah, please.
Just for clarification, so when you give this condition or the information in the previous slide, that is presented after you have given a description, correct?
So the idea would be that we are just going to ask you, say, about a hypothetical candidate, and then we give...
But there is a hypothetical candidate with some description of the candidate, or are you giving this?
This is the description of the candidate, and then we manipulate that description in order to vary the information that we're providing about the candidate. right? And so the idea is that we can go from this text and we can distill this down to, we know, this like single treatment or feature that we're varying across the two conditions. And so we may want to make manipulations about interesting things. Indeed, we all would like to work on interesting things. And what do I mean by interesting? I mean that we would like to focus on interventions that occur frequently in the population of text or in the population of candidates. We want to focus in on the things that actually occur among our candidates. And we'd like to focus on things that have a large effect on individuals' decisions. So those two features are obviously in contrast, in contest with each other. And so while we normally suppose that we know these features beforehand, we design texts and then apply them to these survey contexts and have people respond to the surveys. We're going to invert this approach. What we're going to do is we're going to take a population of texts that we haven't manipulated. We're going to assign them to respondents in the survey. We'll elicit some response. And then we're going to discover the underlying treatments, the underlying features of these texts from using an algorithm in order to do that. So we're going to invert the usual approach. Right? So the key idea, again, is that we're going to have a population of text that we haven't manipulated, and then we'll discover the underlying features based on that population of text. And so what the procedure that I'm going to describe is going to allow us to do is both automatically discover these treatments, and we're also going to be able to credibly estimate their marginal effects, and do this in a way that's going to insulate us from concerns that we might have about p-hacking or other sort of discovery issues that one could imagine would come up in any sort of machine learning setting like this. So to do this, there's going to be 3 key steps to the procedure. So the first thing I need to convince you of is that this is possible. That is, that we can have a randomization at the text level, but we're going to be able to identify the effect of an underlying feature of that text, even though I'm not able to explicitly randomize that underlying feature. So I'm going to give you a set of sufficient conditions to show that this is possible. And I'll show that what we're going to do is we're going to identify a thing called the average marginal component effect, which is the causal quantity of interest from conjoint surveys, which have been recently popular in political science. And so we could think about what this procedure does is offering an unsupervised conjoint experiment. A conjoint experiment is when you offer 2 choices and you sort of have a list of features that you, the analyst, construct. And so here we're saying we don't know what those features are. We're going to discover those underlying features in an unsupervised way. So we show that it's possible. Then I'm going to provide a method for discovering these features. And what this is going to amount to is a method for discovering a mapping from the text to the set of treatments. And a key thing to keep in mind is that while we're going to focus in on discovering a way to do this, you as the analyst set this in the traditional survey experiment. If you run a text-based experiment, you as the analyst are saying, I have this text, and I have a way to map from this text to the treatments that are present in it. Indeed, this is true at any number of experiments we might run. We could have a whole complicated set of procedures, but we might label that just one condition. So we commonly have these sorts of functions in the world. And then finally, I'm going to provide a method for estimating the marginal effect for these discovered treatments. And doing it in a way, again, that's going to give us credible, going to give us valid confidence intervals. Okay, so let's dive right into it. So the quantity of interest we're going to be going for is the average marginal component effect. And so the idea of this average marginal component effect is that we want to isolate the effect of one treatment, holding the other treatments constant. Or in other words, we're going to say, what's the effect of one particular feature of this text, holding everything else constant, and then let's average over all those other features. Okay? And so this is a pretty standard way to try to measure a causal effect in a setting where you have a high factorial experiment. And so to do this, we're going to introduce just a little bit of notation. So we're going to let Zi be a binary feature vector, and this is going to represent the treatments that are present or absent in a particular text. All right, so all I mean by this Zi is, for example, this one right here, which is 5 entries, which has 2 zeros, meaning those first 2 treatments aren't present, then the second 2 treatments are, and then the 5th treatment is not present. Okay, and so we can imagine we have many combinations of this. We can then define the average marginal component effect as follows. So first we can say, for this component K, we can define the response of an individual when component K is set equal to 1, and all the other components are set equal to some value, Z naught K. And then we can subtract off from that the response of the individual when this component is set equal to 0, and all the other features are set to z naught k. So notice there, we just have set the other features to this other value, z naught k. Those are just some combination of zeros and ones. We just say it's something. And then we're comparing the response of the individual when k is equal to 1 and k is set equal to 0. We are then averaging over a distribution of these z naught k's. And this is something that's set by the analyst. And so we can imagine this could correspond to some population distribution. We imagine there's some correlation of features or treatments that exist in the world, and we'd like to represent it there. In many conjoint experiments, this is just a uniform distribution, right, where all combinations are given the same weight. And then we're just taking this average across our population. So again, all we're saying for this causal quantity of interest is that we're comparing the response when this component k is equal to 1 and 0, holding the other features constant, averaging over those other features, and then averaging over our population. Okay, so that's what we'd like to find. We'd like to find this causal quantity of interest, but we're not able to make a manipulation here at z. Remember, I'm randomly assigning people to read whole blocks of text. Okay, so what we're going to say is an individual reads some block of text, and I'm going to represent that with xi. And we could think about xi as just a count vector representation of that text, but we don't even really need to assume that. For the moment, you could just suppose that xi is just some text. And we're going to suppose that zi has lower dimension than xi, which is a supposition that makes sense because we're looking for something that has these underlying features, some distillation of the text. And so what we're supposing is that we have some function that maps from the text to this treatment. That is, I stick in the xi, and out's going to come some zi. And so this function g is going to provide a mapping from those texts to the treatments that are present or absent. It's essentially like the coding rule that's telling you the treatments that are present or absent in this particular text. And so in other words, zi is just a low-dimensional representation of xi. Okay. So we have to assume some things in order to show that we can actually get this average marginal component effect. The first thing we'll assume is that there's no spillover at the text level. That is, everyone's response only depends upon the text that they've read. We're also, because we're running a survey experiment, we're going to assume that we've randomly assigned the text so that there's not people selecting into particular kinds of text. You can make this as a selection on observables assumption. That is, we can suppose there's some features that drive your selection, and we can condition on those. And then everything still works in this proof as well. So those two assumptions are relatively straightforward, and we can believe them because of the particular experiment we ran. This next assumption is very strong and is something that we would want to cast some doubt on, or at least think hard about in a particular situation. And so we have written here a very strong version of this assumption, a sufficiency assumption. And what we're going to suppose is that an individual has the same response to all documents that have the same underlying feature representation. That is, if you have some block of text, two different blocks of text, and those two different blocks of text map to the same zi, to the same combination of zeros and ones, then we're going to suppose an individual has the same response always. And we might think this is a strong assumption because there could be things that we're not capturing in that low-dimensional representation that matter. For example, there could be order effects, maybe there's sentiment that we're missing, maybe there's some image that's accompanying the text that we're not processing as well. All of these things could be violations of this assumption. So there's also a weaker version of this assumption that we could imagine. Rather than saying things hold identically, we could say that this holds plus some error term that has mean 0. Okay? And basically what that means is that there could be some other variation, but that is not important for understanding the effect of the text. Right? So that's a weaker version, but still fairly strong assumption. And all this means is that our underlying representation is capturing everything we need to know about the text. And the final assumption we'll make is that we have common support. That is that all combinations of the treatment have some non-zero probability. And the reason we need this assumption is because we need to be sure that we can disentangle the effects of various underlying treatments. And if this is violated in some way, we usually can redefine the thing that we're interested in order to have it make sense. And so while this is an important assumption, it's not a sort of deal-breaking assumption. And so together, these four assumptions are sufficient such that we can identify this average marginal component effect for some arbitrary k, some arbitrary feature k, even though we're randomizing at the text level. So even though we're not going in and explicitly randomizing these underlying features, we're still able to identify their underlying effect if these four assumptions hold. Okay, so now that we've established that this is possible, that we can go out and identify the underlying effects, the question is, how might we go about doing it? How might we go about discovering these treatments and estimating their marginal effects? So to do it, I'm going to propose both an experimental procedure and then an algorithm that's going to fit in that experimental procedure in order to do this. So the first thing that we'll do is we'll take our corpus of text and we're going to randomly assign those texts to individuals. And then we'll obtain responses from each of the respondents. Again, if we're carrying through this candidate biography example, we're going to suppose that everybody's given us a feeling thermometer rating of this candidate they've evaluated. The next step is that we're going to randomly divide texts and the responses into a training and test set. So we're going to take that pair of information we have, that X and that Y, and we'll either assign it to a training or a test set. And we're going to do this not for the usual reasons that you might think about in a prediction framework, but to avoid two really key issues when thinking about this for causal inference. So the first is that there's a really interesting technical issue that we stumbled upon in this work. And that's this idea of an analyst-induced SUTFA violation. So here's the problem. If we run this sort of intervention, I randomly assign text to people, and I use the entire collection of text in order to discover the underlying features, then it's the case that if I re-randomized, I assign text to different people, I may obtain different responses, and I therefore could obtain different features. So in a very sort of weird way, we as the analyst have induced a spillover where the treatments that we discover depend upon the particular constellation of text that we assign in this particular way. If we randomly divide in this way, it'll still be true in the training set, but we've locked it in place so that in the test set, it won't be the case that the particular features we discover in that the test set will depend upon the particular randomization of the text. So that turns out to be an issue that I think pervades when doing this sort of machine learning intersected with causal inference. It comes up in lots of places. But there's a different issue which I think is like much more plain and something that is pervasive across a lot of other designs. And that is that we'd like to have some safeguard to avoid p-hacking or false discovery in general. So in any setting where I could potentially rerun a model many times over in order to discover the features and then report the interesting effects of those features, there is an opportunity for researchers to get a little excited about exploration and to find things that create the most stars, whatever, in their regression package. And so by doing this, by having the steps, we allow you to do as much exploration you want in the training set, but then you're locked into place for the test set. And so you aren't going to expose yourself to these p-hacking concerns. All right, so now that we have this training and test set, the question is, how can we go about discovering this function that's going to map from the text to the treatments? So we want to use both the documents and the responses because we want to find things that both explain the documents well and explain the responses to those documents, things that are both elicit a large response and are prevalent across our documents. So it would seem like we could do something LDA-like, but the problem with using some LDA-like method is that they embed the proportion of documents onto the simplex, and there's no natural way to get a good causal effect on the simplex using the sort of traditional definitions. You can define some other causal effect, but it ends up not really being the thing that people tend to be interested in. So instead we're going to do some other method, a different method, a thing that we call the supervised Indian buffet process. We're responsible for only 25% of that name, so you can't be mad at us for it. The Indian buffet process is a well-known model from the machine learning literature that's unsupervised and used to come up with a sparse feature representation of text and images and many other applications. So we're going to supervise this in the sense that we're going to include information about the response in order to discover features that do two things. We want the features to both explain the text well and then explain the response well. To do this, what we're going to suppose is that we have, for every one of our documents that are assigned to an individual, we have some underlying feature representation. And that feature representation then is going to generate the texts that are observed. and are going to be used to generate the responses to those texts. So the z vector then becomes the underlying sort of glue across these two components. So there are some non-traditional features here that I'm sometimes surprised that the model works well. So for example, we're modeling xi as a multivariate normal. So we've scaled this so that the text set means 0 in the columns at variance 1. So we still might be surprised that this works well. We have a different version of this that uses a Poisson gamma framework there. And actually, both seem to work pretty well when applied to a variety of texts. Okay. So we're going to use the supervised Indian buffet process on the training set. So we're going to use this to discover some mapping from the text to the treatment. So we apply it. We're going to use it then to infer the latent treatments from the text. So we use it many times over. There's obviously many, many different ways in which we could think about model selection within the training set. So we're going to use a few different ways in which to think about this model selection. So Indian buffet process is a non-parametric model, and so that means that we don't have to set the number of features explicitly. The model will estimate them. Of course, the estimation of those number of features doesn't correspond to some like optimal number of treatments. It doesn't read our mind and know how we want to apply it. So we have to do a little bit more model fit on top of that. So we have a measure of quantitative fit that describes how well these treatments are describing the text that we've observed. And we do a qualitative assessment of the treatments before selecting a final model. Yes?
Can you just explain why this would work better than supervised LDA?
Totally.
Other than providing the number of columns.
Yeah, so it's really a conceptual issue with supervised LDA. And so we have a separate paper where we describe a causal effect of interest. It's just that supervised LDA would embed the text on the simplex, requiring that all the components sum up to 1. This isn't a big deal if you have just a 2-part simplex. So if you're running an experiment, say on kindergarten, you want to know what's the optimal balance of boys and girls in the kindergarten classroom, then you just know that if you bump up boys, you decrease the number of girls, and that's okay. But now imagine you want to run an experiment where you want to ask, what's the optimal balance of kids that come from low, middle, and high income families, right? And so you say, okay, I want to run an intervention where I bump up the number of low income children. Necessarily that decreases the share of middle and high income kids, but you have to know what's the balance there. There's actually, of course, an infinite number of ways in which you could think about balancing that. You obviously have some degrees of freedom because we're moving kids around here, but that's sort of the issue. So you have to write down some different causal effect. As you marginalize over that, the sort of marginal effects that we define here aren't defined for the simplex.
The output would be something. It'll give you.
So you could use it to get the sort of ideas about what's in the text that's describing the responses. We want to use this as well as this sort of coding exercise. So we want to pick it up and apply it in the test set in order to learn the treatments that are present. And so you could, again, with this other causal quantity of interest, think about using it there. You just have to sort of shift the quantity of interest in one that's not quite as natural. So I think there's other ways in which one can think about doing this. So anything that would provide, any method that would provide you with either this like binary representation of the text or some sort of continuous version that wasn't constrained, you could do that as well. We don't have a continuous version here because for this initial exercise, we didn't want to get into the stronger assumptions you have to make about the shape of the relationship, but you could definitely do that as well. So I think there's a lot of features of this that are modular in the sense that you could just fit in something that you think works better, and like that first proof works because all we're doing now is just finding that function G. Okay, so now that we have this function G, this mapping from the text to the treatment, we want to infer the treatments in our test set and we want to measure their effect. So what we do is we take the supervised Indian buffet process that was trained on the training set and we apply it to the test set without conditioning on the test set responses so that we don't end up in a weird situation where we end up with different treatments for the same text if they had different responses to them. And so once we've done this, once we've made this inference, we have inferred the set of treatments that are present in the text. We can use that as if we were running any other experiment, right? We're empowered to run any method that you want to at that point, and you can infer the causal effect of those treatments in any way you wanted to. What we do here for the results I'm about to show you is we estimate the treatments with a regression, so simple regression. But we also include a bootstrap to include two different kinds of uncertainty. We have uncertainty about the treatments that we're inferring, And then we have estimation uncertainty from that regression, like you would if you ran any other experiment where you knew the treatments that were present or absent. So our bootstrap's going to take into account both those kinds of uncertainty. Okay. So let's put this all together into an experiment that we ran. And so we did this with a set of candidate biographies, and we scraped these candidate biographies off of Wikipedia. And so this contains a great deal of information about the candidates. This is candidates essentially a little bit before World War II until the present day. And so you have someone like Barbara Mikulski, who was a senator from Maryland. And we became concerned that if we left the original names in place, that somebody may infer something about the candidate that they would know that wasn't included in the text. So if they knew Barbara Mikulski well and they really loved her, maybe they would give her this a high evaluation, which would have nothing to do with the background. So we engaged in this laborious permutation of names, where Barbara Mikulski became Barbara Schumacher. Even though we're moving from a Polish to a German name, we tried to keep this within ethnic groups as well, in order to keep it plausible. People have been surprisingly pushed back on the Mikulski-Schumacher thing. I would just say, I think it's reasonable. So we deliver this information, and specifically what we did is, for a set of respondents in a survey that we ran with SSI, we asked each respondent to see up to 3 texts from this collection of 2,200 biographies. So what they would do is they would observe the text, they would give us a feeling thermometer rating from 0 to 100, and then we would use that as the inputs to the procedure I just described. So we had under 1,900 participants and a little bit over 5,300 responses from those participants. We divided them evenly into the training and test set. So we used the training set, we applied the supervised Indian buffet process, inferred the features, and then used that to code the test set documents to learn the features that are present or absent, and then to infer their effect.
Are you collecting any more demographic information?
Yeah, so that's a good question. We, for the purposes of this study, did not collect more information on them. So we had a partner who was also running on the second half of the study, so we would have other information that's available, but we're not exploring any sort of heterogeneity in response here. Okay, so what do we find? And so for this sort of experiment, I generally think it's useful that we find things that seem to go along with sort of like late night comics assessment of what people like in a politician. So here we're showing the estimate of the causal effect of these features, and then a 95% confidence interval. And so we find that people dislike lawyers and career politicians. So that's what feature 9 and feature 5 describe. And then people tend to like folks who have education. That's what feature or treatment 3 is describing. And folks who have served in the United States military. So in treatment 6 and 10. So we may wonder or worry about this sort of overlap between feature 6 and 10. So the thing that I think is going on here, and that probing seems to suggest is happening, is that because we're looking at members of the House, congressional candidates, who ran after World War II, we had such a large collection of people who had military experience, because basically there was a time period where everyone in the US House had served in World War II, or close to it, that we have lots of opportunity to discriminate between 2 different kinds of service. We could have people who both enlisted, as in treatment 10, and people who were officers in the military, like treatment 6.
Justin, you're not specifying the number of treatments here.
So we need not do that, but in the end we picked 10 treatments. So we selected a model with 10, but we fit many, many different models in the training set in order to come to that number of 10.
And how did you come to it?
Yeah, so we went through this extensive number of model fits where we sort of fit the model a number of times. So there's several hyperparameters that you could integrate over, but we left to tune. So we fit them with those tuning parameters. And then we use this quantitative fit to say within this genre, what's the model that had the highest quantitative fit? And then across those, we sat down and made a qualitative assessment across these, one that seemed to have the best semantic coherence once we were sort of reading those biographies. But then, so once you do all that sort of manual work and extra model fit on the training side, it's just picked up and applied on the test side, so it's like locked in place. So in one way to think about it is it's sort of an exploratory and indirect machine learning way to do a lot of the sort of treatment construction that you might do if you did many, many pre-tests, but it's sort of like machine-guided pre-testing is what's going on in the training set.
How stable are these?
Yeah, so it turns out that these are fairly stable. So we have a group at NYU who replicated this, and so they seem to have gotten the same sort of results. And so you can rerun this and you tend to get the same sort of treatments. But stability in this, I think, is in general a pretty big issue, as it is with all of these sorts of models. And so one of the things we're working on right now is initially running on the entire data set in just an Indian buffet process. Because if you don't include the responses, there's no concern about the analyst-induced SIFA. If you do that and then use that as a starting value for the supervised Indian buffet process in the training set, that's going to stabilize things pretty substantially on top of like already what I think is a fair amount of stability. Yes?
It's kind of a simple question, but how did you pick your participants?
Sorry, pick the what?
Your participants for the...
Oh, yeah. So we recruited them through the Survey Sampling International. It's a survey firm, so they do the recruitment for us. They maintain this like online panel. And we say, okay, we want this to look, we want this to be quota matched to look like the US population. Yep.
Are you plotting like the regression coefficients here, or the actual change in the feeling thermometer?
Yeah, so this is like the actual change in the feeling thermometer.
Okay.
Mm-hmm.
Are you just computing the linear component here? So let's say you had a descriptor that received a university education, but is a member of the NRA. Do you get then a modulatory interaction?
Yeah, so for this model right here, we are just including the first order components. You could definitely include these second, third order components, look for the interactive effects. The reason we didn't do that is because very quickly you're going to run into sparsity issues. You don't have a lot of those interactions, so you'd have to fit a model that's going to make stronger assumptions in order to figure out what those interactions are. But you definitely could do that. It would just be like many other models that
So what's going into your error bars? They're pretty substantial.
well, they're pretty substantial because they're zoomed in. So I guess I could zoom out and make them look smaller. But what's going in the error bars are two things. So we're trying to be honest about the error that's present, and we have an extra layer of error that an experiment normally wouldn't. And that extra layer of error is that we're inferring the treatments that are present in these texts. And we're doing that based on the inference from the supervised Indian buffet process. So we make some inference about the treatments that are present or absent from the text. And basically what we're doing there is we're taking draws from a distribution, a posterior distribution on this text. And then once we have that, conditional on having that, we then have the normal estimation of certainty you'd have in any experiment. But because we do that first step many times over, that adds some uncertainty. Yes?
What is the relationship between feature prevalence and treatment effect? So in the sense of, it seems like here you're discovering features that appear sufficiently often in the corpus, and also they have a treatment effect, but there could be other features that you do not discover that may have a larger effect than some of those you identify here. Is that the case?
Yeah, that's definitely true. And so it's like this sort of like classic question about what do you identify, and so it could be something that has a massive effect that only appears once. And the question is like, do we care about that? Is that something we want to focus in on? And I think a supervised approach where we just go in and say, this is the thing I care about would be important. I think another thing that's absent from the features here that we may care about are certain race and gender characteristics. Just because of the history of who was in Congress in the latter half of the 20th century, those tend to be washed out. And so that's another thing that we might care a great deal about. So we could think about doing even a sort of hybrid approach where you would have go in as the analyst and say, these are features that I care about. I want to fix the fact whether or not this describes someone as a man or a woman, or this describes their racial group, and then I want to discover these other features as well. So that's something you could do in the model. Yes?
So, I mean, for the ANSI, you're assuming a uniform prior over the Z naught K, all the other features there. How much does that matter? So clearly it doesn't necessarily hold. There's going to be correlations between, I mean, say 6 and 10 or
yeah.
6 and 10. So, I mean, what's your sense of how much do you lose with that, or how much does that affect the results that you're kind of assuming uniformity when?
Yeah, so I think this is a really interesting question. So here we're actually assuming the correlation that's present in the text. And so normally in the conjoint you assume this uniform. And so we'd actually have to re-weight this a bit to go back to the non-uniform case. And so I think this is actually a benefit of what we're doing here, is that we're adhering to the weights that are present in the text. So if we're worried about this sort of situation, if we're worried about the case where we need to reweight our Z0 case to look like the population, then we can make appeal to what that population looks like. So we could say, I have census data. This describes people who are going to opt into this job training program are going to be receiving this sort of message. Or another classic example from this fantastic paper by Jens Heinmuller and Dan Hopkins, where they look at the attributes of immigrants that folks would like to admit or not to admit to the United States. There you could reweight that population to look like the kinds of folks who are applying to enter the US. So I think that's a concern. And it's also sort of like weird or different to think that these effects could be dependent upon this other population. There, I think it just depends on being clear that there's this reweighting happening.
How would you handle that sort of population reweighting in a case like this, where you've got discovered topics, so you can't really say how topic 6 apply to census data necessarily or something?
That's right. So we could say something, though. We could go back in and say we know the population of people who serve the U.S. military and who have the kind of education that would get you labeled in treatment 3, and people who are career politicians. And so we could go in and try to reconstruct that. I think the bigger concern here is that we reweight off of the correlations that happen in the text to some other correlation. Perhaps the uniform would be the natural one. Say, I don't want to base this on the weird correlations that happen in this population of text. I want it to look more even. I want to give every feature, make every feature equally likely. And that reweighting, I think, would be the one that's
less.
No, please.
Correlations coming off of the training set or the test set, and does that introduce any?
So it's a random split across the two, but it's got to come off the test set, right? So the correlation is going to come across the things that we're inferring.
And how important are the individual keywords? Is there any way to get coefficient sizes for individual keywords?
Yeah, so I think this is like a really fantastic question, and one that sort of takes a step back and think like, what are other ways that one might go about doing this? And so initially, if you think about this, you would say, oh, if I want to know about the causal effect of some text, I'm going to run a lasso regression where I'm going to have the response on these words. And the reason that we don't want to do that is because it isn't clear to us conceptually what that would mean. And what do we mean by it's not clear conceptually? I mean, if I, for example, drop law or not from a text. So suppose that turns out to be something that's important, and so I imagine my intervention is I let law appear or not in the text. But I still have law school, that bigram, and I sort of juris doctor, student, that sort of thing appearing. I'm still conveying the information that you went to law school. And so I think that conceptually becomes difficult to think about. So I think it's difficult to think conceptually what it would mean to assign the coefficient to just the word law school, because normally we don't think about that as an intervention.
It would be hard to change those many keywords in order to make a passage compared to.
So you could describe someone as being a lawyer or not. That's the idea. And that would be the intervention. Is that this right? So not just these keywords, it's that you're conveying this entire idea, and these keywords are just indicative of this being present there.
But that's again based on your interpretation and based on your background knowledge of how you're interpreting that.
Yes, absolutely. Yeah. So this is a fantastic point, right? Which is going to be true of all of these sorts of unsupervised models, is that they are dependent upon some extra analysts sort of like reading them, squinting, reading the tea leaves, as the classic paper says. And so what you can do with all of these settings, and indeed something we're working on right now, is you can run this initially, you get a whole bunch of ideas about features, and indeed you get some that are important. I encourage you to pick this up, and you can design a traditional experiment where you're actually manipulating these things and really pegging this down and saying this is the causal effect. And there's no reason to stop us from doing this sequence, and indeed if you run this sequence where you have training and then test and then a supervised experiment, you have lots of reason to believe that you found something real. And I think it's a very valid criticism here, is to say like, well, this depends upon your reaction to it. Also, if you can post these things into the replication archive, then other people can read them. I mean, it becomes like a place where reasonable people can disagree. Mm-hmm.
I'm wondering how you dealt with some hidden features that don't have text representations, for example, gender.
Yep.
Because gender, for example, would not be detected as a treatment according to our personalization, but the same would be negatively correlated with, for example, like military or distant treatments.
Yeah. So that's missing here, and the reason that's missing here is because there just aren't a lot of women in the House during this time period, the time period we're looking over. And so again, what I think we could do is we could go and either fix it, we could say that this is present or absent manually, and then run the same procedure on everything else, but ensure that that treatment's there. But at the moment, it's just something that's being ignored. It could be a violation of that sufficiency condition, and perhaps this is biasing the results one way or another, we can imagine.
I'm sorry
Yeah,
to ask
please.
some questions.
Yeah.
So you said that individual words don't necessarily have coefficients.
In this framework, they don't. So we're thinking about these like underlying features. Yeah.
How are you, for example, in topic 3, you were having 6 words, whereas in topic 5 you have
Oh, yeah. So let's think about where these keywords come from. This is just coming from a matrix that is like the topic matrix in LDA, except it's this feature matrix, and we're just picking the top words here. In the paper, we have the rest of those. I think they got suppressed here just for space concerns, like sloppy slide creation.
LDA, they have weights.
But, sorry, but the things that I'm describing there, those weights, are not going to correspond to an effect of the word. Yeah, they're corresponding to the thing that's giving rise to the text. So you have a linear combination of these columns that then generate the text. So there, certainly, we can get weights there, but that doesn't correspond to the effect of it. Yeah. Okay. Yes.
Going on the previous question, so when you randomize the name, you change the last names in order to retain anonymity. Did you keep the sex the same so that people was always, so the subject was always aware of the gender of the person that they were reading?
Yeah. So we didn't change the first name. We just changed the last name, which is like part of what led us to have to think really hard. So you didn't end up with like weird name combinations. Okay. So I'm just going to conclude real quick, and then we can maybe I can answer some more questions. So there's lots of future directions here, and I think there are a lot of applications of this idea in lots of ways we can improve what we're doing here. So there's a number of things that we can do. So like empirical tests of the key assumptions is something we're working on, and we're also working on a paper that sort of clarifies some subtle issues but important issues in doing causal inference with text, like this analyst-induced SUTVA violation and how to do causal effects with LDA. There's also an interesting issue with ensuring that we actually have a well-defined G function that we're working on as well. We have a different treatment discovery method that I mentioned before that's based on a Poisson gamma framework. And we can actually think about applying this in non-text settings as well, but there's also something high dimensional. I think the best example of that might be with images, where if you do an image experiment, you can imagine there's actually many things varying in the background, and we may want to try to uncover the underlying features of that image. But it could work with perhaps voting records as well. And finally, an application, a way in which we're thinking about this is situating it in a broader framework. So here we've worked on this as text as treatment. So some of you may have encountered the structural topic model from Molly Roberts and collaborators. And there the text is the outcome, and you have a sort of traditional quantitative experiment. But we can think about extending this framework to have text as both the outcome and the treatment, and think about ways in which we might come up with categorizations so that we can discover both the text as treatment and the text as outcomes. We begin thinking about the conditions so we can model conversation with well-defined causal effects. So that's what I have. Thank you very much. Love to hear some more questions.
Yeah, I have a brief question. It's like, so it's a generative model, and like you could actually like after the fact, even though you have attributes like, okay, this is the lawyer topic, or this is the sort of an illustrated topic, and you can come up with your own treatment. Have you like thought of like having the model come up with the treatment, and then you do the retest and do control?
Oh, that's cool.
It's like
for
text generation.
Yeah.
Is getting better, I guess.
Yeah. I think that we would need a better generative model. So, or we would need to think about it, like we could take draws from the model, but we would need to think about a way to make it a coherent sentence would be really the key. We could think about doing something like that where it was a bit more sparse and we created something that looked more like a content. I think that would be feasible. That's a good idea.